All right, so put a 3 in front of the Na, okay? What's what's next? A 2 before the H3PO4. Alright, let us try. So you have 2 there. Okay. Yes, that's it. Just give me a second, please. Alright, so that's for the normal salt. All of the hydrogen ions would have been replaced in the original acid. Now we're gonna do an acid salt. So I'm gonna use back the same salt, so we can form multiple, sorry, the same acid, because we can form multiple different salts here. So it's H3PO4. What else do we want to react it with? Yes, other than a metal. Or we can use back the same. Okay. Yes, remember that metal oxides are basic. So yes, that's okay. Alright. What do we form? So we have an acid plus a metal oxide reacts to form. Yes, so what's the salt? Mg3PO4. Yes, it would. Yes, it would. Thank you, Ranil. Because magnesium has a 2 plus charge, you know. That's magnesium, Mg2 plus. PO4 is 3 minus. That is why in phosphate there are 3 hydrogens, because phosphate is a polyatomic ion with a 3 plus charge. Yes, same here. See the 3 or so again? It's all because of the charge. So it's PO4 3 minus. And the charge is switch. And that's how we get that. Alright, so we get magnesium phosphate plus water, so salt plus water. Alright. But remember that we didn't want to form the normal salt, no, we wanted to form the acid salt. So I'm just going to do another equation here. How would we form the acid salt? So acid salts are formed when the hydrogen ions are in an acid are only partially replaced. So how would we form that acid salt? Originally we had 3 hydrogens, but if we choose to only partially replace some of those hydrogen, what would we do? Alright, I'm gonna go ahead. So originally it would have been 3 hydrogens. In acid salts, we don't replace all 3 hydrogens. So let's say we choose to replace only one of those hydrogens. Right? So if we replace one hydrogen, that means we are gonna have 1 sodium. And if we take out 1 out of the 3 hydrogen, that means we have 2 hydrogens left back. Because 3 minus 1 give 2, so it would be 2 hydrogens left back. And then our P, oh my bad, I forgot it was magnesium. Let me do an eraser. Alright, so for this one we can't exactly have it as is. Like, notice we have 3 hydrogens. We can't replace, let's say, we can't just replace all 3 per se. We can't just replace 1 hydrogen. The reason being is that whenever you have a compound, the charges in the compound have to balance out somehow. So notice that in this top one here, it would have been magnesium. And just pay attention and go with me. So you have magnesium, it's a 2 plus charge. This goes back into redox. 2 plus times 3 gives 6 plus. So we have 6 positive charges. Note that phosphate is a 3 minus charge. So 3 minus times 2, that would have given you 6 minus. Right? So the charges cancel in ionic compounds. Right? Same down here. Note that magnesium would have had a 2 plus charge. It's only one magnesium. Hydrogen would have had a 1 plus charge. And phosphate overall has a 3 minus charge. Note that once again the charges cancel out. We all see that?
Yes, please.
Okay. Right, so that's why it couldn't have been written like Mg2H. It would have been really incorrect. There would have been too many charges on our left. Too many positive charges. So this is the correct way to write it. And then I'm just gonna write my water. If it were sodium, now I'm gonna do one with sodium because that one is a bit simpler. So if it were sodium, so H3PO4. Alright, so what's an acid salt that we could form? Anybody? What's the acid salt that we form? If we have 3 hydrogens in the original acid, but that's a normal salt, Renil. We want to form an acid salt. So what do we do? In acid salt, you have the hydrogens in the acid only partially replaced. So how many hydrogens do you want to replace in this acid? Guys, if we have 3 hydrogens, you get to choose how many of those hydrogens you want to replace. Do you want to replace 1? Do you want to replace 2? Or do you want to replace 3? Okay. Yes, sir. Because you choose to replace 1. So you yes. And if you choose to replace 2, what is it going to be? Yes. Guys, you know I gave this to you on an exam. Your class on an exam. Alright, so it's you would have said Na2HPO4. So yes, the first one would be a normal salt. This one would be a normal salt. Since all of the hydrogens are replaced, we're not seeing any hydrogen, so it's a normal salt. And these two, once you see the hydrogen, just know that it's an acid salt. So these two are our acid salts. Alright. Does anybody else want me to do another example, or we're okay with this? Alright. Continuing, so it says the active ingredients in Gravico and gestid is sodium carbonate, Na2CO3. By the way, what is the chemical formula for sodium bicarbonate? So that's sodium carbonate. What's the chemical formula for sodium bicarbonate? Na2S2O3, that's sodium thiosulfate. What is sodium bicarbonate, which we call baking soda? How do I write sodium bicarbonate? No, that's sodium carbonate. Na2CO3 sodium carbonate. Somebody look it up and tell me, please, what is sodium bicarbonate? Yes. What is sodium bicarbonate? The sodium bicarbonate is NaHCO3. Yes. We also call sodium bicarbonate sodium hydrogen carbonate. So just in case you hear about this, sodium bicarbonate or sodium hydrogen carbonate. This is what? This is the chemical compound that's in baking soda. Right? Another question I have, what's the charge of carbonate? It is 2 minus, yes. So bicarbonate is 2, carbonate is 2 minus, sodium is Na plus. And if you were to look at all of this, note that the charges will cancel, would get a neutral charge for the overall compound. Na is 1 plus, hydrogen 1 plus, carbonate 2 minus, it's going to equal to 0. So I'm just putting what I did earlier into perspective. Alright, continuing on the question, it says a sample of gestid was added to dilute hydrochloric acid. The volume of gas produced was measured every 30 seconds for 240 seconds, and results recorded in table 1 below. The experiment was repeated with Gravico. The figure shows the volumes of gases produced in the syringes by gestid at 4-time intervals. So, what's the volume here? Yeah, they don't have it. So what's the volume here at 60 seconds? Eighteen and a half. Okay. 18. It is in between, yes. So 18.5. What's this one? Yes. Next one. Mm-hmm. And the next one. Right. Okay, so that's what we have there. So it would have been recorded in the table. Let us just continue. Using the axis, and that's just 4 marks, and 4 marks you just put in your values. Using the axis provided in figure 2 on page 7, plot the graph for the data obtained for gestid. Table 1, the graph of Gravico has already been plotted for you. Oh, so we need to just plot on the same graph. And this is quite convenient because they already gave us the title, they gave us the unit on each axis. So all we need to do really is to just plot the graph. What am I going to do? So I guess I could split my screen. Alright, so the first one is 0 to 0. Can someone take a screenshot and help us out, please? So let's take a screenshot of the values and let us work together. Done? Alright. So the first one is 0 to 0. What's the second one? I think it was 30 to 10. 30. What was it? 30 what seconds? Alright. Know that I'm using back similar points that they used. Notice. Alright, next. What's the next one? 60 to what? Wait, what? Oh, it's here. Okay. So 60 would have been 18.5. My bad. Let me just write it in. I think it was 18.5, 25.5, 27.5. Okay, so you said it's 60 to 18.5. 60, 18.5 is gonna be about, so 15, 16, 17, 18.5 is about here. Oops. Alright, so I have my 18.5. What's the next one? Okay. 90 to 25.5. Okay. Yes, continue. So it's falling 22.5 to what? 32? Okay. You know, I plotted that point earlier incorrectly. You said 25.5, right? Mm, so this is 25. Yeah, 25.5 would be here. That's all. I don't know. This graph is really hurting my eyes. 20. This is 25. 21, 22, 23, 24, 25. The point earlier would have been 25.5. So it would be here. This is 25.5. Okay. Um, I really doubt that this would have been 18.5 as well. So 15, 16, 17, 18.5 is here. And the second point would have been what? 30 to 10. I think that would have been correct. So now we're at the sixth point, Roger. 27 or 37? Okay. 26, 27.5. Next. 180 to 40. Next. 210 to 41. Next. Alright, I'm gonna double check this point right here. And the one for 150. It's 30. It's not 27, it's 37. Alright, 35, 36, 37. Okay, thank you, Reggie. Let me just draw a curve through my points. Note that this does not look like a straight line, so I'm not really drawing a straight line. It's gonna be a curve. 18.5, 15, 16, 17, 18. No, that's it. We're going up by every 2. I am sure. See it here. Alright, let me go over this side. So this is 15, 16, 17, 18, 18.5, 19, 19.5, 20. You see that now? Okay. It's Reggie. These lines are just doing whatever they want to do. Guys, it's not going to be perfect, but we get the concept. And I think I can guess what question they're going to ask next. But let me ask you guys, what do you think they're going to ask? It's a rate graph. Once we see something about volume and time, it has to be something dealing with rate. So what's a possible question that we could expect? Yes, what's a possible question that we could expect based on the graph alone? You haven't been watching any YouTube videos or reading the textbook? What's a possible question? Alright, I am going to ask it then. I'm going to ask the question. What part of the graph shows the fastest or the fastest rate of the reaction? Let me just change this. Somebody? Yes. So the initial part of the graph is when the rate of the reaction is the fastest. Why? So right here going here. And usually once you can like use a ruler and draw a line through it, that would have been the range. So if let's say this, notice that this gives me a constant straight line. So all of this is a fast rate. But then once it reaches somewhere about here, it starts to deviate from my straight line. So I could say that from 0 to about 25, that's when the rate is the fastest. So once it begins to deviate from that straight line, that's where I would say it begins to slow down, right? Now from here, when you start to see it curve off per se, that is when the reaction slows down. So I'm going to say here to here is when it slows down. And how do you know that the reaction has stopped? What straight line? I have a lot of straight lines. What straight line? Okay, so we have a constant volume towards the ending there. That's suggesting that the reaction would have stopped. So here to here, that's where we're no longer producing any more gases, which means any more gas, which means that we don't have any more reactants present in our conical flask or in whatever container that they're using. That's when everything just stop completely. Yes. So let's see if they have any questions similar to what we just analyzed. So it says using graphical graph, deduce the volume of gas produced at 135 seconds. Show how you obtained it. So at 135 seconds, the volume of gas, 135, say it's 120. Alright. So somebody try to figure out where 135 would be, please. 135. The middle line. Let me see. So 120 divide, wait, the 120 plus 150 divided by 2. Yes, it would be the middle line. Halfway between would be here. Alright, so the volume of gas, I think this one would have been the gravical one. And they want us to show it, so you use your dotted lines and you try to show it as boldly as possible, and you indicate what it is. So 135 seconds. So you're right, you would write in sentence volume of gas produced at 135 seconds. In this case, what's the volume? Guess what's the volume? Yes, it's 40.5. Alright, let me just write that in here. And imagine just 2 marks to put some dotted lines on the graph and write the answer. And I'm going to write my volume as well. Alright, so it says using your answer in BIII, calculate the number of moles of gas produced at RTP for the Gravico reaction at 135 seconds. How could we calculate the moles of gas? Let's see if you're thinking. How could we calculate the moles of gas? Once you see something about gas, what's the equation that you use? Guys, give me 1 second. Good evening, everyone. Yes, it is Chagina. Chagina, yes. Thank you for having me. It's my second time here, and I feel amazing to be a part of this meeting. Awesome. And please tell me that you're aspiring to become a Toastmasters before the Toastmasters year is ending. Yes, absolutely, absolutely. All right. So, can you assure me that you or maybe he can reach out to you for confirmation? Yes. Yes, sure. All right. Awesome. Lisa Wood. All right. Guess what's the equation? Volume of a gas equals Alright, and since we're just solving for more, this is what we're going to make the subject. We can just we can add everything around it. So volume of the gas that they gave us would have been 40.5 centimeters cube. Now, anybody remembers the value of RTP? Before I even add this in, what's the value of RTP? 24 dm cube. So the value of RTP is 24 dm cube, but the volume that they gave us is in centimeters cube. What do you want to do? Because it has to be the same unit. What do you want to do? What are you going to divide by 1,000? Okay. So you could have done it, you can do it this way, or you can choose to convert the RTP into centimeters cube. It would give you the same answer. So you said divide this by 1,000. Let me just put that in. All right, and then this is going to be 0.00. That's all? No, man. Yes, thank you. DM cube. Yes, can somebody work out our sulfur mole, please? Yes, what is my answer? 0.00168. That's what you said? Okay, so I'm just gonna round up mole. Thank you. No, that's the unit for mole is MOLE. Sorry, MOL. Alright, now the next one, that's just 2 marks. Write a balanced equation with state symbols for the reaction between HCl and sodium carbonate. So HCl, what's the state symbol for HCl? Okay. Yes, and we have plus. What's the chemical formula for sodium carbonate? Yes, so it's Na2CO3. Alright, so you guys got something similar on the exam, you know. Alright, so what are we gonna form? We have carbonate plus acid. What's the state symbol of the carbonate? Sodium carbonate. It is not solid. Why is it not solid? I believe the rule says that all carbonates are insoluble except carbonates of sodium, ammonium, and potassium. You guys can go and fact check me. But as I said earlier, as long as you see sodium present, potassium, ammonium, I think question was saying something earlier, but as long as you see any of those present, it has to be soluble. Was it question who was saying something? No man, somebody does say something. I heard something. Okay. So as I said, as long as you have sodium present, it's going to be soluble. So this is AQ as well. Guys, give me a second. Amisha call. Okay. Awesome. Yes. So this is aqueous. So sorry about that. So this is aqueous. And we have what are we gonna form? Sodium chloride plus what? Yes. And what else? Something is missing. Yes. State symbols for each of these, please. Alright, so this is gas, this is liquid. And guys, even if they don't ask you to write the state symbols, write them. Please to write them. That's once it says balance equation, it automatically means that you need to write the state symbols. Always write those. What's my state of the sodium chloride? Yes, it is. Yes, it is. Note that the water is present. So yes, it is aqueous. Alright. Balance it for me quickly. Come on, guys. Quick, quick, quick. Check who is here. And I think that's it. Thank you, Roger. Guys, if you're not sure when you're balancing and you see a lot of oxygens. Oh, sorry. You know, I really meant Renil. I am so sorry, Roger and Renil. Thank you, Renil. Guys, if whenever you're doing balance equations, always balance or try to balance the metals first. They're always the simplest to balance. So your metals and you work your way across the periodic table. So like you know how you write from left to right, metals come first, then the transition metals, then you have nitrogen, etc. So try to balance the metals first, then you can the second to last thing that you balance would be the hydrogen, and the last thing, the last thing is the oxygen. Usually you don't even have to balance the oxygen because once you balance out everything else, the oxygen just automatically becomes balanced. Alright, so that's 3 marks. 3 marks to put in state symbols, balancing, and also writing the correct chemical formula. So the next question says determine the number of moles of sodium carbonate that reacted at 135 seconds. So I'm just going to give you a minute to think about it. How are you going to calculate the moles of sodium carbonate? Look at what you have so far. So you look at the mole ratio. In this case, know that earlier I would have calculated the mole of the gas. Hoping that it's the same one, but this is a 1. Based on what we have for the gas, it's a 1:2. For the carbonate, 1:1 mole ratio here. So it says determine the number of moles of sodium carbonate that reacted at 135 seconds for the Gravico method, Gravico reaction. Why divided by 2? Alright, so look up here. What did you find the mole of earlier? Was it the HCl? It wasn't the HCl, so it can't be. It cannot be. See it here, the gas. Moles of the gas. This, the carbon dioxide being the gas. So we're using what we know to find out what we don't know. In this case, we know that the ratio is 1:1. Oh my gosh. Alright. It would be the same. So since it's 2 marks, I recommend probably writing a little statement. Let me just change colors. Says 1 to 1. So we have 1 mole of sodium carbonate reacted to give 1 mole of carbon dioxide. So since we formed this amount of mole of carbon dioxide, and it's a 1 to 1 mole ratio, therefore we're going to have the same number of moles of sodium carbonate reacting. Now I want somebody to put that in a statement. Yes, what's the statement? Yes, somebody, what could I say to tell them that this is the amount of mole of sodium carbonate that reacted? Tell me your reasoning. Alright, I'm going to start. Based on the mole ratio, one molecule or 1 mole of Na2CO3 reacted to give 1 mole of CO2. Therefore, if the moles of CO2 produced was 0.0017 mole, the mole of Na2CO3 is also 0.0017 mole. And if it were a 1 to 2 mole ratio, you know that you would have to probably do some form of division or multiplication depending on where that number is. Alright. A question that they could also ask you is to determine the mass. Sometimes they don't tell you they don't ask you to determine the moles. They just ask you straight ahead to determine the mass of sodium carbonate. So how would I calculate the mass of the sodium carbonate? Yes, how do I calculate the mass of the sodium carbonate? Mass equal what? Mass equal moles times molar mass. Yes. And the moles that we have is 0.0017 mole. Molar mass of sodium carbonate is what? I'm gonna let this be the only question I work tonight, and then tomorrow, I don't want to make promises, but hopefully I can keep a streak and we come back again. So what's the molar mass of sodium carbonate? So sodium is, I believe, 23.4, somewhere thereabout, and I think yes, they would. Sometimes they ask you to solve for it, or they give you the overall molar mass, but I gave you the question, so I want you to solve for it. Practice makes perfect. See if me scroll and them oh, look at that. See what I said? Notice what I said earlier? They gave you you have to calculate it on your own. You know, I could write CXC myself. So 23 times 2 equal, and then that's 46 plus carbon is 12, and then we have 3 oxygens. 3 times 16. Yes, it's 106. Yes, Roger. Alright, so it's 106. See how simple that be? Guys, don't be like me and write the answer. Only show the working. That's why they gave you this. Notice how them give you the values and look at that. 2 marks. However, still show how you get the answer. How you get the 106. Always show it. So let me just actually put it in bracket. So it's so them is 23 times 2. This would have been a double bracket here. Plus 12 plus 3 times 16. And so we get 0.0017 mole times 106 G mole. And the answer that's our answer, grams. And I think this question is complete like this. Oh, we have something else. From the graphs obtained in the investigation, Maxine suggested that gestid is the stronger antacid. State whether you agree with Maxine and give one reason to support your choice. Yes, guys. So why is gestid? I believe, oh, this is graph vehicle and this is gestid. Let me just double check. So Maxine says gestid is the strongest acid. Tell whether you agree or disagree. Strongest antacid. So which one is the strongest one? Why? Anybody else? Anybody else? Nobody really? Nobody else? Let me just look back on the question. So what's a strong acid? You're saying if it's the same thing as a strong acid? What's an antacid? Remember, antacids are used to neutralize the stomach acid, so no, an antacid is not an acid. An antacid would somewhat be of a base, hence the sodium carbonate. Sodium carbonates act as bases, but they aren't really bases. They're used to neutralize acids. But when you think about the strength of something, just to deduce, when you think about the strength of something, you're not talking about the amount of volume it is present. So it's a bit different. Strength has to do with, how would I put it, the amount of hydrogens present per se. But this is a base. Alright, so Roger, your first answer would have been correct. And it's not really the explanation that you were saying. So the reason why, so remember, as we said earlier, let me just type it. The antacid acts as a base, right? As a base to neutralize the acid. The stronger or the strongest antacid would mean there are more basic ions present to neutralize the acid in the stomach. If more acid ions are neutralized, hence more gas is produced. Therefore, the gravical curve would suggest it's being the strongest antacid. I think that's the only way I can actually explain it. Does that make sense? So it says antacid acts as a base to neutralize the acid. Right? The strongest antacid would mean that there are more basic ions present to neutralize the stomach acid. So we're having more basic ions to neutralize the stomach acid. And the more acid ions you're neutralizing, the more gaseous ions, or the more volume of gas you're going to produce. Hence, the curve looks higher for the Gravico method. So the strongest antacid would in fact be Gravico. Yes. Yes, it would be. That's what you had said? Yes, it would be. Do we have time for another question? Let me see if this is too much. We can, all right. We're going to go up to 8:30. Just 8:30 and we go. So using your answer, oh, we finished that already. Students were asked to observe strips of yam placed in a container of distilled water. After 20 minutes, one student suggested that osmosis was occurring in the yam strips. Define the term osmosis. What is osmosis? All right, that's 3 marks. They're being so generous with this question. All right, state what the students would have observed after 20 minutes. What would be observed? Yes. Mm-hmm. Outline how osmosis supports the particulate theory. Mm-hmm. So it simply says explain how osmosis relates to the particulate theory. I can't see the question. But outline how osmosis supports the particulate theory. You don't have to. You really don't have to. Because it's asking about osmosis. But if you want to use it, you can. Yes. So yes, Roger, what was the answer? There's something I need to correct you on about the definition. High concentration to an area of low concentration. I think my sentence wording is incorrect, but I think we get the gist of it. Presence of empty spaces between particles. Okay, yes. So what you gave for the definition, the movement of water molecules from an area of high concentration to an area of low concentration to a cerebral membrane. Okay, it's alright. It depends on how you give it, This is correct. This is correct. But if you were giving it in the perception of more concentrated solution that has a high concentration of solute, then it would have been the opposite, of course, because the water would move to the area of high concentration of solute particles. So it depends on how you're giving the answer. But this is correct as is. That's why I had to double check. Not sure how many persons understood that, but this is correct here. The yam strip, which was a solid, was placed into distilled water that is a liquid. State how the arrangement of particles in a liquid differs from that in a solid. So what's the arrangement? In a liquid, yes. Somebody?
Miss particles in a liquid. It's not close together, but they are able to move freely as each other.
However, particles in a solid are tightly packed and are closer together than in particles in a solid are only able to vibrate. Alright, that's 2 marks. Yeah, I'm gonna leave it at that for this evening. Hoping that you guys would have probably studied periodicity already. So tomorrow we continue on this. This paper looks really interesting. Alright, so have a good night, everybody. Any questions before we go? Mm-hmm. I think you have a chance. Yes, I do. I think you have a chance. Yes. Yeah. Because some of the inorganic part is just common sense, you know. Some of it is just common sense. But you need to deduce and reason out what is really happening here. For some of it, of course. But I advise you to still study. Study the inorganic section. Read about water, green chemistry, the metals. It's not as difficult as you think. I sent a video on their reactivities. It's not as difficult as you think. And you need, go ahead. Oh, I see. I see. I have, okay. I somewhat agree with you, but you have to find interesting things. So I could try a little something and see if it gives any piques a little bit more interest. All right. Any more questions? All right, everybody, good night.